Hello, welcome to Quick Guide to Quantum Mechanics. So in quantum mechanics, the solution of Schrodinger equation is a very important one. This basically gives you the energy of the state. Now, there is a very important concept in quantum mechanics is the degeneracy. It refers to a situation where two or more different quantum states of the system have the same energy level. These states are said to be degenerate, and the number of such states sharing the same energy is called the degree of degeneracy or simply the degeneracy. This plays a very important role in the quantum system, especially condensed matter physics and astrophysics. So it can explain conductivity, chemical forces, along with it can explain the behavior of stellar objects. A simple example one can take that you are solving Schrodinger's wave equation. H psi is equal to E psi. So Hamiltonian operator is operated over wave function. This gives us energy eigenvalue. Among the set of energy eigenvalue, it may happen for different quantum states, different psi states having same energy values. A classical examples one can take. You can having a 5-storied building having total 10 flats, where flat A having 1000 square feet and flat B have 1500 square feet area. So you may at different floors, but flat A values for ground floor, first floor, second floor, third floor having same rental. Whereas for flat B of different floors having same rental value. So this rental and the energy values are equivalent in these cases. Whereas the floors are representing the different psi states or quantum states. So the flat and its carpet area and the rental value, it's equivalent to the degenerate quantum states. Now we'll take some examples of degenerate and non-degenerate quantum states. Now to explain this thing, we'll consider the simplest quantum mechanical problem of potential box, one-dimensional potential box. We all have read about one-dimensional potential box in quantum mechanics in undergraduate courses, where potential is 0 within x equal to 0 to x equal to L, but outside the potential is very large. So within this region x equal to 0 to x equal to L, the wave function is available. And the particle, the quantum particle having potential 0. So it acts like a free particle inside the state. But outside the potential box or at the boundary, there is no existence of wave function. X less than 0 or x greater than 0, you don't have any wave function, non-existence of wave function. So simply by using this boundary condition, one can solve the Schrodinger's time independent equation. The solution gives you the wave function psi is equal to root 2 by L sine k into x, where k, the wave vector, is quantized in nature. K is given as n pi divided by L. So pi is constant and L is the length, where n is some discrete values. This gives you the state. So if n equal to 1, n equal to 2, n equal to 3, for different values of n, you are at different the quantum states. So when n equal to 1, this will be psi 1, n equal to 2, this will be psi 2, n equal to 3, this will be psi 3. And the wave function values will be different. So these are the wave function. When n equal to 1, n equal to 2, n equal to 3, n equal to 4, you will get that wave function. And obviously, the the density, the probability density is the squaring of that Obel function. So this gives you the probability of finding the particle in different quantum states. Now the most important part is about the energy. As we have discussed, the potential within the box is 0. So the particle within this box is act like a free particle. It is having only kinetic energy. So when you try to calculate the energy, it comes in this. N square, H square, 8 ml square. So now H is Planck's constant. 8 is a constant number. M is the mass of the particle. If you are taking electrons, so this will be electron's mass. And L is the length where the particles are happening. So this gives you the energy value or the energy eigenvalue of that system. Now again, if you put n equal to 1, so this will be H square, 8ml square. Now if you put n equal to 2, this will simply 2 square or 4 into E1. Then put 3, this will be 3 square, 9, 4 square, 16 accordingly. The most important part is that we are at different energy states and having different energy value. So a potential box, one-dimensional potential box gives you a non-degenerate condition. Here energy values are not same for any of the quantum states. Now we can see the next case. Now you have a potential box, a cubical potential box, a three-dimensional potential box. Now again, the concept is same along x direction, y direction and z direction. The constraints are given and the particle act like a free particle within the box, and outside the box there is no existence of the quantum states. Then solve the equation, one can get expression something like this. So this is simply for x-axis 2 by Lx, for y-axis 2 by Ly, and for z-axis this is 2 by Lz. So it will simply 2 cube means 8 Lx, Ly, Lz. But as we have considered for the three-dimensional cubical system, so this will be L cube. Now the next part is the energy eigenvalue. The most important one is the energy eigenvalue. So when you are calculating energy, it's simply a repetition for the three different directions. So this is h square 8m, n square Lx square plus m square Ly square and p square Lz square. So n, m and p are denoting different quantum states along different directions. N is for x, m is for y and p is for z direction. Now if the system is a cubical one, so obviously you can take L common. We are applying this condition, you can take L common. So h square 8m L square can be taken as common and n square m square plus p square factor will be there. Now we'll try to calculate for the different quantum states. If you put all 1, n, m and p. So this simply gives you 3 into E1. We have already considered this factor as E1. So here the degeneracy or the degree of degeneracy is 1. But try for the first excited state where we have taken 1, 1, 2. Means x-axis this is 1, y-axis this is 1 and for the z-axis this is 2. For the other combination 1, 2, 1 or 2, 1, 1. X, y and z, the combinations are different. So this obviously this will give you the first excited state. So what will be the energy value? So in all cases this will be 1 square plus 1 square plus 2 square. So 4 plus 1 plus. So this gives you 6 of. How many combinations are possible there? There are 3 combinations are possible and this is known as the degree of degeneracy is 3 in this case. You can check it for the second excited state. 2, 2, 1 or 2, 1, 2 or 1, 2, 2. You will get the 9 into that energy. So obviously there will also be 3, 4. Third excited state, the same 311, 131, 113. This obviously gives you the 3 combination, 3-fold degeneracy. But for the fifth excited state, this is 2, 2 and 2. The only combination possible. This is 1. And for the sixth excited state, this is 321, 312, 231, 213, 132 and 123. So these are the combination for sixth excited state. So XYZ values are different in this case. So how many degrees of degeneracy is there? 6. And the amount of energy is 1 square plus 2 square plus 3 square. This is 14 of grams. Now we can see we are at different energy states. So psi values are different. This is psi 0. So this is psi 0, psi 1. So for different psi 1, you will have same is for the second excited state, third excited state and the sixth excited state. You can also calculate for the higher excited state. So now energy values are equal for different excited states. Obviously, so this is a great example of quantum degeneracy. Why degeneracy is important? Degeneracy often gives the idea about symmetricity. It explains the symmetricity of the quantum mechanical system, the spherical symmetricity of atom. It explains or it basically influences the quantum mechanical system, atomic spectra or transition probability. Okay, so when you are applying electric field and magnetic field, the energy level splitting was explained by the Zeeman effect and Stark effect. So it also explains the partition function of statistical mechanics, which explains entropy, specific heat and thermal properties of matter. Now in modern day application, the qubits important in quantum computation. So the quantum error calculation, it plays a very, very important role. Now in case of solid state, band structure, Fermi level energy and semiconductor physics, it plays a very, very important role. Degeneracy specify electron degeneracy pressure. It is an outward force that counteracts gravity and prevent white dwarf from collapse. So in a celestial body, it also plays a very, very important. So today we have discussed about degeneracy. So what is degeneracy? It's the same amount of energy in different quantum states. Thank you.